All right, guys. So in today's video, we're going to be going over section 7.2, day 2. In the previous video, we were looking at Reese's Pieces and seeing what proportion of them were orange. In this video, we're going to be looking at do Skittles or M&Ms have more orange candies? So it says Mr. Wilcox believes that Skittles have a higher proportion of orange candies than M&Ms, while Mrs. Gallus believes that the opposite. So who is correct? Now it says take a simple random sample of 50 Skittles and a simple random sample of 50 M&Ms. Calculate the proportion of orange candies in each sample and find the difference between the proportions, Skittles minus M&Ms. So let's say, for example, I've got 50 randomly chosen Skittles and 50 randomly chosen M&Ms. And within each one, I'm going to count how many orange pieces there are. All right, so for the Skittles, let's pretend that I have 13 orange pieces out of 50 total. So that means I'm going to have a proportion of 0.26. And then for the M&Ms, let's pretend I have 9 out of 50, which is 0.18. All right. Now, because I have two different proportions here, 0.26 and 0.18, I want to be able to tell the difference between the two. So I'm going to say that the Skittles proportion is going to be p hat 1, and then the M&M's proportion, I'm going to say that is p hat 2. All right. Now, if I want to count the difference between them, okay, all I got to do is just take 0.26 minus 0.18. So my difference in proportions is going to be 0.08. And we're going to call this p hat 1 minus p hat 2. All right. Now, it says write the difference on a sticker dot and place a dot on the board. If we were in a physical classroom, we'd be able to do that. But every single person would have a difference in proportions, and each dot would be placed on the board. But I've just gone ahead and made an example here. So let's say that this is what our class is going to look like. So I've got, I've got numbers ranging from negative 0.08 to positive 0.12. So I've got a dot on negative 0.08, 1 on negative 0.06. I've got 3 on negative 0.04. I've got 4 on negative 0.02. 5 on 0. I've got 6 on 0.02. 4 on 0.04. I've got 2 on 0.06. 2 on 0.08. And 1 on 0.10 and 0.12. All right, and then don't forget, we got to give it a title. This is a sampling distribution of p hat 1 minus p hat 2. And now number 3 says, what does each dot represent? Okay, so kind of like last time how we said each dot represented a proportion of pieces, proportion of orange pieces in 50 pieces of Reese's Pieces. And so on this one, since we're looking at a proportion and we're doing p hat 1 minus p hat 2, it's going to represent the difference in proportions of orange candies for one sample of Skittles and one sample of M&Ms, because those are the two samples that we're looking at, right? So it is the difference in proportions of orange candies for one sample of Skittles and one sample of M&Ms. All right, and number 4 says, for the dot plot above, make a prediction about the following. So shape, if I come back up here, it looks like it's going to be about normal, right? So kind of have a single peaked, unimodal, symmetrical shape, right? So we can assume that this is going to be approximately normal. All right, and then the center looks like it might be around 0 or 0.02, somewhere around in there. So we can kind of estimate, we can just say it's something like 0 or 0.02. We're not trying to be exact here because we're just kind of eyeballing it, right? And then variability, it looks like if my center is about right here, right, then I might think that my variability might be upwards of like 0.06, 0.05, somewhere around in there. So, and the reason is because you're kind of looking where the graph kind of starts to level out. So it looks like it starts to level out around in this area. So I'm going to assume that my variability is about 0.06. Now it says a Google search reveals that 21.6% of Skittles are orange and 20% of M&Ms are orange. So number 5 says, describe the sampling distribution of the sample proportion of orange for Skittles, and we're going to call that X, and the sampling distribution of the sample proportion of orange for M&Ms, and we're going to label that Y, for samples of size 50. So remember how we have conditions that we have to check, right? One of them is large counts, whenever we're looking at large counts. And then obviously we also want to look at the mean and standard deviation. Yesterday when we were looking at Reese's Pieces, the orange candies in Reese's Pieces, we calculated these things. But because we're looking at both Skittles and M&Ms, we're going to need to be able to check these things for both of them, okay? So remember, if you're doing shape, okay, this is large counts. Okay, so for the Skittles, we have to show that NP is greater than or equal to 10, and then we also have to show that N times 1 minus P is greater than or equal to 10, okay? So we have a sample of 50, and we were told that 21.6% of Skittles. Okay, so this is going to be our P1. P sub 1, we assume is going to be 0.216. So we're going to have 50 times 0.216. And if we do that, we're going to get 10.8, which is in fact greater than or equal to 10. Now, if we do N times 1 minus P, we're going to get 50 times 1 minus 0.216. And if we do that, we're going to get 39.2. And that's also greater than or equal to 10. So the Skittles work. And then if I'm looking at M&Ms, okay, remember, still the same formula. NP greater than or equal to 10, N times 1 minus P greater than or equal to 10. And so I'm going to have 50 times our true proportion of M&Ms we're assuming is 20%, so that's going to be P2 is equal to 0.2. So 50 times 0.2 is going to give us 10. And that's greater than or equal to 10. And then the other one, 50 times 1 minus 0.2. And so we're going to get 40, also greater than or equal to 10. So since both of these sets, both of these samples pass both inequalities, we can say that both of them are going to be approximately normal. All right, now if I'm trying to find the mean, okay, so remember that mu sub p hat is going to be equal to p, whatever we assumed the true value is going to be. So the mu sub p hat sub 1 is going to be equal to p sub 1, and we assumed that the true proportion is going to be 0.216 for Skittles. And then mu sub p hat 2 is equal to p sub 2. And we assumed for the M&Ms it's going to be 0.20. And then standard deviation, if I'm trying to find standard deviation, the equation is going to be sigma sub p hat is equal to the square root of p times 1 minus p divided by n. Okay, so if we're doing it for the Skittles, mu sub p hat 1 is equal to the square root of 0.216 times 0.784 divided by 50. And that's going to give us 0.0582. And then for M&Ms, we've got mu sub p hat 2, which equals the square root of 0.2 times 0.8 divided by 50. And that's going to give us a standard deviation of 0.0565. Okay, so we've estimated the shape of both distributions and we found the mean and the standard deviation of each. And so what I want to do now, number 6 says, describe the sampling distribution of the difference between proportions of orange Skittles and M&Ms. So X minus Y. So if we're looking at the shape, okay, if both samples are approximately normal, then we can assume that the difference between these samples or difference between these proportions are also going to be approximately normal. So because we passed the large counts conditions for both samples, we can say that this shape for the difference is going to also be approximately normal. Now, if I want to calculate the mean of the difference between the proportions, okay, I'm just going to have the mu sub p hat 1 minus p hat 2, okay, remember difference, is going to be equal to, it's just p1 minus p2, whatever we assumed their true values are going to be. So in this case, the Skittles was 0.216, M&Ms was 0.2, so we're going to have a difference of 0.016. And then if I'm calculating the standard deviation of the difference between proportions, okay, since we're doing a difference, the equation is going to look a little bit different. It's sigma sub p hat 1 minus p hat 2. It's going to be the square root of, we've got our first proportion, p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 divided by n2. And all of that is within the square root. So if I plug all of these values in, I'm going to have 0.216 times 0.784 divided by 50 plus 0.2 times 0.8 divided by 50. So I'm going to have a standard deviation for the difference of 0.0812. All right, now, Mr. Wilcox and Mrs. Gauss calculated a difference between proportions of 0.08. From their samples, calculate the probability of getting this difference in proportions or higher. All right, so if I'm trying to calculate the probability, because we found that this difference is approximately normal, we can assume, or we can calculate this using a z-score, okay? So I'm just going to draw a graph. Okay, so in the middle, we've got our difference of means of 0.016, and we're trying to calculate the probability of getting 0.08 or higher. So here's 0.08, and we're just calculating the area under the curve at or above that. Okay, so other thing I got to write inside, I've got 0.016, comma, 0.0812. And so here's our mean, our standard deviation. And so if I'm trying to calculate a z-score, okay, for a difference, I've got p hat 1 minus p hat 2, so the difference in proportions, minus p1 minus p2, so our mean, divided by our standard deviation. And so if I plug all of this in, okay, p hat 1 minus p hat 2, that's just the performance we're measuring it at. So we are measuring at 0.08 or higher. So I'm going to have 0.08 minus p1 minus p2, that's just our mean, so 0.016. And then divide that by our standard deviation, which we said was 0.0812. And so we're going to get a z-score of 0.79. And if I want to calculate the probability of getting at or higher that 0.79, we can use table A. And since we're measuring at or above, we'll have to do 1 minus. So whatever value you find on your table for 0.79, just do 1 minus that. So if I'm doing table A, I'm going to have 1 minus z-score at 0.79 gives us a value of 0.7852. And so our probability is going to be 0.2148. Okay, so there is a 21.48% chance of getting a difference in proportions of 0.08 or higher. Okay, and so when you're doing a difference of proportions, you can have a positive difference or you can have a negative difference, all right? And depending on how you set it up, tells you which one will have a higher proportion. So if you have a positive proportion, in this case, a positive proportion of 0.08, because we're doing Skittles minus M&Ms, X minus Y, Skittles minus M&Ms, that would tell us that Skittles have a higher proportion of orange pieces. Now, if we got a negative proportion, okay, then since we're doing Skittles minus M&Ms, that would tell us that M&Ms would have a higher proportion. So in this case, we are looking at a 21.48% chance of getting a difference of 0.08 or higher. That means 8 percentage points more Skittles have orange pieces than M&Ms do in this case. All right, so a couple of important ideas to take away. Number one is the sampling distribution for p hat 1 minus p hat 2. All right, so if you're looking at the shape, all right, it's approximately normal if both conditions are met, or if the large counts condition is met for both samples. So we'd have to see that N1 P1 is greater than or equal to 10. N1 times 1 minus P1 is greater than or equal to 10. And we also have to see that for N2. So N2 P2 greater than or equal to 10. N2 times 1 minus P2 greater than or equal to 10. For the center, okay, so the mean, mu sub p hat 1 minus p hat 2 is just going to be equal to p1 minus p2, whatever the assumed true value is. And then variability, we've got standard deviation of p hat 1 minus p hat 2 is equal to the square root of P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. Okay, and the other learning target for today, number 2, normal calculations. So if you are able to prove that the shape for the difference is approximately normal, okay, so we assume that it's going to be approximately normal, right? In the center will be your true value, P1 minus P2. And let's say, for example, it really doesn't matter where it is. If you're looking at something else, this might be p hat 1 minus p hat 2. It's your observed value. Okay, let's say I'm trying to calculate at and below that. Then if you're calculating your z-score, oops, one more thing. So okay, you've got your mean of the difference. And your standard deviation of the difference. All right, if you are able to show that it is approximately normal, then you can calculate a z-score for it. So we've got z is equal to p hat 1 minus p hat 2 minus p1 minus p2, all divided by your standard deviation. Okay, so if we're going to check our understanding, it says at Westville High School there are 315 seniors and 389 juniors. 65% of seniors have parking passes, and 42% of juniors have parking passes. The statistics teacher selects a simple random sample of 30 seniors and a separate simple random sample of 30 juniors. Let p hat sub s minus p hat sub j be the difference in the sample proportions of seniors and juniors that have parking passes. What is the shape of the sampling distribution of p hat sub s minus p hat sub j, and why? So if we are trying to find the shape of it, okay, remember, we're just trying to prove that it's approximately normal. So we have to do the large counts rule for both samples, okay? So I have to show that n sub s times p sub s, okay, is greater than or equal to 10. And we have to show that n sub j, well, let's do it this way. N sub s times 1 minus n sub s, p sub s, is greater than or equal to 10. And then we also have to show the same thing for the juniors. N sub j times p sub j is greater than or equal to 10. And n sub j times 1 minus p sub j is greater than or equal to 10. Okay? So for the seniors, I've got 30 times 0.65 because we've got 65% of the seniors and then 42% of the juniors. So for seniors, it's 0.65, and I'm going to find 30 times 0.65 is 19.5, and that's greater than or equal to 10. And then if I'm doing for 1 minus, I'm going to have 30 times 0.35, and I'm going to find that to be 10.5. So that works. And then if I do it for the juniors, I'm going to have 30 times 0.42. And that'll give me 12.6. So that's greater than or equal to 10. And then if I do 30 times 0.58, that's greater than or equal to 10, because that's going to be 17.4. All right, so because the conditions are met for both samples, we can say that this group is going to be approximately normal. All right, now it's asking us to find the mean of the sampling distribution. So mean is just going to be the difference of the two, right? So mu sub p hat sub s minus p hat sub j is going to be equal to 0.65 minus 0.42. So we're going to get a difference of 0.23. All right. And then if I'm doing, it says calculate and interpret the standard deviation of the sampling distribution. So we've got p hat sub s minus p hat sub j. And we're going to have 0.65 times 0.35 divided by 30 plus 0.42 times 0.58 divided by 30. And so we're going to get a standard deviation of 0.1253. And so if it's asking to interpret, we can just say the difference in sample proportions who have a parking pass, because that's what we're talking about, right? Typically varies by about 0.1253 from the true difference in proportions. So typically varies by about 0.1253 from the true difference in proportions. All right, and part D says, what is the probability of the difference in sample proportions, seniors minus juniors, of students with the parking passes is greater than 30%? So we're trying to find that what are the odds of having a difference of 30% or more? So we assume, okay, remember we saw that 0.23 was our difference in proportion means, right? So if I create a normal curve here, we're going to have 0.23 in the center. And we're looking at greater than 30%. So 0.3 is going to be about right here. And we're looking at what are the odds of having above that. Okay, so remember, N is, we said our difference was 0.23. Standard deviation, our mean was 0.23, standard deviation was 0.1253. Okay, so because this is approximately normal, we can calculate a z-score for it. So z is going to equal 0.3 minus 0.23 divided by 0.1253. So we're going to get a z-score of 0.56. And because we're measuring at and above, we're going to have to do 1 minus when we calculate our p-value. So if we're using table A, we're going to have a p-value of 1 minus. On a table A z-score of 0.56 gives you a value of 0.7123. And so we're going to have a p-value of 0.2877. Okay, so there is a 28.77% chance of having a difference in proportions of 30% or greater between seniors and juniors parking passes. All right, so that is the end of these notes for section 7.2 day 2. We're going to be looking at, on the next one, is section 7.3.